Okay, good morning. Can you hear me? Can you see the blackboard?
Yes.
Okay, thank you. Now, there's another quiz. As I told you yesterday, it's open you today and tomorrow, and I think you have 2 days to finish it. It's 30 minutes. I put additional scores yesterday on your second exam scores. What else? What else? Today I will talk about periodic motion. Tomorrow I will talk about gravity and sound, waves and sound. So I have 2 chapters tomorrow, but they are very small, just selected topics. And their math are not complicated, and you don't need to do anything difficult. Okay. Today we'll talk about periodic motion. We dealt probably before with 2 kinds of motion. First one is the linear motion, like this. Then we deal with the rotational motion. It is just like this one, as you see. I think you can see that online, yes. So we have linear motion and rotational motion. Now we have another motion, which is a periodic motion. This periodic motion means the object that moves, it repeats its motion during a time. During a time. For example, when I walk like this, go on backward, forward like this, it's a periodic motion. If there is a fly, for example, flying like this, and repeats its motion always and always, it is a periodic motion. Yeah. Just recording now. Yes, thank you for that. I didn't stop it like yesterday. But for the recording yesterday, I have the same lecture from the previous year, from the previous semester. It is uploaded, and I put the link on Canvas. You can watch it. Okay, now for a fly, it is repeat its motion, but it is not uniform as we see. There's no, yes, we have period of time, but it is not uniform motion. For example, we have uniform motions, just like, for example, Earth around the sun. It is a uniform motion. I think it's in this direction, or depends on the way how we look. Okay, and its period is equal to 1 year, as you know, right? Also, the sun rotates around the Earth, but during 1 year. Another thing, you know the clock. Now the clock has 3 hands. One of them is 4 hours. It rotates its total motion or total rotational motion during 12 hours. It's a periodic motion. The minutes hand needs 60 seconds, 60 minutes, right? To repeat that one motion. The second needs 1 minute to rotate, to finish just one rotation. So there is difference in velocity. You know that the seconds hand pointer has the most velocity, then the minutes, then the hours. And we have an example to solve it about this. In our study, we will study also the spring system. If we have a spring with a mass, and you will see that in the lab, I think, or it does not exist in someone, but maybe you will see it. You see it in previous semester. Spring mass system. Without any forces, we have, this is the rest situation, the rest state. Okay, if we push this system or we pull it and release it, it will start vibrating. This vibration is a periodic motion, which is a simple harmonic motion. Okay, this is for a spring. Also, you will see, we will study today, we have something named pendulum. It's a string, massless string, and a mass. And this mass is vibrating between 2 points. We will do that today. Okay, to study some properties of this motion, which is a periodic, it is not a linear and not a rotational. The rotational motion can be considered as periodic motion because it is repeating itself. But if we have just one rotation, it is not a periodic motion. Okay, we need to study this motion property. What is the time to repeat our motion? What is the something called the amplitude? For example, if for this pendulum we have another distance, maybe another experiment, we will pull this mass for a further distance. So we need to study. It is a wave, okay? As you see here, I draw a wave, and this wave is related directly to simple or to periodic motion. Okay? Let us see this. I have a spring, and there's a mass hang to this spring. I think you can see it. Well, okay. This motion now is periodic motion. Yes, it is a periodic motion because it is repeating itself. Now, the position is changing downward and upward, as you see. So this is the position axis. The time is changing in this direction. As we know from before, in physics, we don't use x, y, we use anything on the x-axis, another quantity on the y-axis, and we did that many times. Now we have the time with position. You can consider position x or y or anything you want. Look at this motion. It is the same. I just draw our motion, draw our system on an x position versus t graph. I can increase the motion by pulling the mass farther way down or a little bit closer to the rest position. The rest position is at this position, which is 0 here. Okay. As you see, the motion is repeated itself after a point. This point is here. Then we can see a copy of this motion. For this part of our system, we call this part a total wave. A total wave. And this total wave has some properties. For example, for this period, we are on x, on time axis in this case. This period called t, which is period. It repeats itself at each period t, the wave repeats itself. Okay. Now, sometimes we put x here, which is the length for this wave. In this case, if we take x, which is the position on x-axis, then this wave has, for the total wave, has a wavelength. Wavelength. It has a sample lambda. Lambda. It is a wavelength. For example, I'll remove this also. We have X here, and we have amplitude here. I will talk about amplitude now. For example, if this is 1 and this is 2, and we have this wave, for example. This wavelength, which is the total length of this part, which is the total part, lambda, is equal to 1 meter. So the wavelength of this wave is 1 meter. But if I draw another wave, like this, as you see, this is a smaller wave or a shorter wave. It has its length like this. This lambda is equal 1 over 2 meters. It's a different wave and the different properties for this wave. Maybe we will see this wave, for example. This wave, maybe it has lambda equal to 2 meters. Okay, so we have long waves, we have short waves, as you see here. For long waves, for example, like the radio waves, okay? Keep it later, I will talk about it. Now the waves. This is the time period. Maybe if we have the time axis on the horizontal axis, maybe we have also this wave. We have another period. Now the amplitude is the distance from the rest position, the origin. This is the amplitude. Amplitude. We call it A in our relations. Okay. We have something also. So in each one period, we have one wave. In one period, we have just one wave. This period in seconds. But if I ask you how many number of waves per second in 1 second, this means the frequency. I'll remove this. F, the frequency. So if you have the time period for the wave T, then the frequency is equal 1 over T. The unit of the frequency is 1 over second, because the time is second, 1 over second, or second to minus 1, or we have another name which is hertz. If you hear about this unit from the radio station, it's hertz. It's number of waves 1 second. Any question about waves? I'll talk also about it. For example, if we have this wave also. If you need to start from the 0 point here and end with this point, it is a total wave, lambda. It needs one total full period. If you start, for example, from any other point, you need to go to this point, identical point, then you will have the same lambda and the same time period. If you start, for example, at this point, when you will repeat your motion, it is at this point. So we have, this is lambda, which needs total full period. Okay? Now the amplitude is the maximum displacement from the origin. Okay? Now I am on page number 2. As you see, page number 2, we have number of waves with different wavelengths and time periods. Now we have a connection between rotational motion and the wave motion or the periodic motion. Any question about waves? We have a mass, and this mass is rotating about a center of rotation, and we have okay, now this mass is rotating. And omega for this mass, omega, which is the angular velocity, as you know, it is delta theta over delta t. I have it here, yes. There is a relation between omega and the change in theta, and this is theta. If you look to this motion from a side, you will see the mass going up and down, just like that, from a side note, okay? Going up and down, it means just a periodic motion, just like the experiment I just did, like this, okay? So, if the mass is here, then the motion we are here. If the mass is here, then it is at the amplitude displacement. If the mass is here, or here, then our motion is here, and so on. For this motion, we have a frequency, which is 1 over t. The 1 over t is equal to the frequency. There is a relation between omega and the frequency. If the omega is faster in rotation, then the vibration is faster. And we have, look, if we have omega larger, faster, then we have vibrations more waves in just 1 second. So we have a relation between omega there is a relation between omega and theta and the frequency. It is omega equal to 2 pi multiplied by the frequency. 2 pi, it is the total rotation of our motion. So for omega, if we rotate one total rotation, which is 2 pi, as you know, 2 pi is one rotation, 360 degrees. Then we have 1 unit of the frequency. For one rotation, we have 1 unit of frequency, 1 hertz. Okay? So this is the relation between omega and the frequency. But the frequency is equal to 1 over t. So also you can put it like this. We have these two relations. They are the same. Omega is equal to 2 pi multiplied by the frequency, which is equal to 2 pi over tau. Now I think we have an example, yes, which is the clock example. Any question about this? Again, don't forget the evaluation. Okay, we have the clock. We have, this is the minute. This is the hour hand, and this is second. We need to find this motion property in the clock. Okay. The period for the second hand is equal to how much? 60, yes, right. 60 seconds. The period for the minute hand is equal to 1 hour, which is equal to 60 minutes, which is equal to 3,600 seconds. We need more time to complete one vibrational motion or one period. Okay, the time period for the hour is equal to 12 hours. But from here, 1 hour is equal to 3,600 seconds. So it is 12 multiplied by this, which is equal to 43220 seconds. 00 second. This is the time period for the hour R. Okay, what about the frequency? The amplitude depends on the length of that arm. The amplitude is the distance from the origin. Okay, I'll use this relation now. What about the frequency now? Frequency for the second arm is equal to 1 over t, which is 1 over 60. No, this is for a minute, 60 seconds. Which is equal to, it's given here or not? I'll calculate it. 1 over 60, it is something 16. 1 over 60, it is equal to 0.01667. What is the unit? It is hertz, or second to minus 1, or 1 over second. What is the frequency for the minute? R is equal to 1 over t, which is 3,600 seconds, which is equal to 1 over 2.778, we approximate, multiplied by 10 to minus 4 hertz. It's very small, the frequency. What about the frequency for, okay. What about the frequency for the hours? Is equal 1 over that big number, which is 43200 is equal to something small, 1 over 2.314 something multiplied by 10 to minus 5 hertz. It is small. Needs more time to repeat one motion. Okay, what else we can find? It's a simple question. It's the kind of questions that come in the exam. Okay. Let us find omega. In 2 ways. I will find it by one of these things, one of these relations. Omega, which is the angular velocity for the second arm, is 2 pi multiplied by the by f. This is f, which is 0.01667. We need just to multiply by this, which is 6.28. 2 pi. So 2 pi multiplied by 4 over 60. Simply, it is equal to 1 equals 0.1, no, 1. 0.1047. What is the units of angular velocity? It is radian per second. It is velocity, but it is a radian, not meter. What about the angular velocity for the minutes arm? It is equal to 2 pi multiplied by its frequency, which is 2.778 multiplied 10 to minus 4. It is equal to 0.001745 radian per second. It's a small velocity. What about the angular velocity of the hour? Again, it is 1.4544 multiplied by 10 to minus 4 radian per second. So I just gave you the system. All of us know about this system. We know the time period for this system. After that, we compute everything. Any question about this? Like, we have another example, which we need to solve this example using the graph. I'll give you a wave, and I will ask you to tell me the properties, the quantities. I'm on page number 3 now. This is another example. I have 3 waves. Small one, another bigger one, another bigger one also. we have here the time. I think this is the time. Yes, this is time axis, seconds. This is 1 second. No, yes, this is 2 seconds. And so on. We have the small wave is the wave number 1. The bigger wave is wave number 2, and the biggest wave is wave number 3. Okay, what we need to find. I have a table, period and the frequency. Okay, I'll draw this table. We have the smallest wave, we have the bigger, and we have the biggest. How much the time period for each of them? For the smallest wave, we need a total wave length. For this smallest wave, this is a total wavelength, which is this one. Okay, can you see it? We have, this point is 1 second. We have 2 waves of them. As you see, we have 2 waves in 1 second. So how much the period? We have 2 waves in 1 second. So what? I'm asking about just 1 wave. How much time it needs? It needs 1/2 of this second. Okay. What about the other wave, which is this one? This one. I'll draw it like this. Yes, it's clear. I'm asking about the second one. During 1 second, I have a full wave. So the wave is 1/1. I will put it 1/1. Because I need to ask about the frequency. I need to flip the quantity. What about the bigger wave? The biggest one. The biggest one, we need 2 seconds to finish it. So the time period for the third wave is 2 seconds over 1. Everything is over. What about the frequency? The frequency is equal 1/t. Okay, 1/t, it is 2/1. This is 1/1. It's still 1. This will be 1/2. That's it. If I ask you about the angular velocity, you can't find it, right? Any question? As I told you from before, we have the periodic motion. This periodic motion, sometimes it is not uniform, just like a flying in the room. It is not uniform. But when the wave is a uniform and we can put a relation to describe it, it will be another thing. And we start studying it, which is, for example, the motion of this spring or the motion of this circle. Its name is, any question about this? I'll move everything now. We have something called simple harmonic motion. Simple harmonic motion, it is a simple vibrational motion and can be described by a relation. This relation is sine and cosine. We know the sine and cosine from before. And the simple harmonic motion, it page number 4 and the beginning of the page, the next page, which is 5, we have something not to derive, but to show from where is the origin. But I can give you the relations. But I will tell you, if we have this spring and we have a mass, as you know, we have the Hooke's law. Hooke's law. The Hooke's law is talking about the force of the spring, which is Hooke's law. It is equal to negative K, which is the spring constant, multiplied by the distance x, which is the compression. As you see here, I have in my hand a spring. I don't know if you can see it. It's here, okay? I have this spring. It has a constant K. I have also this spring. Both of them are springs, but K, which is the constant for this big spring, is different than the K or the spring constant for the small one. If K is big, then the spring is difficult to be stretched or pushed. Also, if the K is small, then it's easy to play with this spring. Is this clear? Now, this is about K. We talk about it from before, and we solve examples, and we see that in the examples. We have a mass now. It is hanged to this spring. This is one system. So this mass will accelerate because we have a force coming from the spring, and they are connected. So we have Newton will come and look at our system, and he will put his force now. It is equal to the mass multiplied by the acceleration. We know that all of our acceleration and motion in x direction. I don't need you to put yourself in difficult case, but the acceleration, as you know, it is the mass multiplied by dv by dt. D is delta v by delta t. This is the instantaneous velocity. If we need to put x there, it will be the mass d2x by dt squared. It is the second derivative, and it is not required in this class to talk about this, but I need to show you that there is the acceleration has a relation with the position, and the two forces are the same because they are connected for one system. So we have at the end we have the force is equal to the force from the spring, which is equal to the mass multiplied by the acceleration. The acceleration is the second derivative of x. There is a relation between them, and I will divide over m. I will move this to there. So I will have this relation finally, d2x by dt squared plus k over m. X is equal to 0. If you hear, I think you did in math about differential equations. This is the differential equation. It is solving x as a function of time. In our solution here, x as a function of time. We know how to write x as a function of time from before. For example, we have x as a function of time is equal to x naught plus v naught t plus 1 over 2 a t squared. This is x as a function of time. We talked about this previously. Because x naught, v naught, they are the initial position and velocity. It is known, and the acceleration is the acceleration, which is a constant. So x depends directly on the time. Also here, we have a solution for this. We don't need all of this. We need just to know the solution. It will be given to you anytime you need to solve an example. It is a cosine omega t plus 5. Don't be afraid, it's simple. Phi inside the cosine, it is the starting point of vibration. You see my drawing, always I start from 0, from here. So phi is equal to 0. But if I start from here, then I have a different phi. In my questions, in our study, phi is always equal to 0. But you will still see it in the notes, phi. But keep in your mind, we need phi always equal to 0. Okay? What about A? We just talk about A. We don't need all of these derivations. This is the way. This is A, which is the amplitude, which is the maximum displacement from the origin. Okay? What is omega? So A is the amplitude. Omega. It is the angular velocity. But in vibrational motion, we need to give it another name because it is relating to the frequency. We give it angular frequency. Bingo, same velocity. Okay. T is the time. Cosine is cosine. Phi is 0. So this is the position. And you need just to put numbers here. If I give you the amplitude, omega is equal to 2 pi f. Also, it is equal to 2 pi over t. Now, in this system, you see my final equation is d2x by dt squared plus k over t, we'll call k over m, x equal to 0. This is omega squared from my relations. So omega also equal to the square root of k over n. All are given in the next pages. You can see them in the table, and it is simple to beat. This is for a spring system. We have an example. But before that example. Now, again, we have the position as a function of time. It is the amplitude multiplied by cosine something. This something is omega, which is omega as we know it, 2 pi f or 2 pi over t or k over m. You can find it by any way. Multiplied by the time. Plus 0, something 0. This is x. We are physicists now. We don't just find the position of the motion. If I ask you about a particle or object is moving, vibrating, I am not asking just about the position. Sometimes I'm asking about the velocity. I'm asking about the acceleration. Okay. So what about the velocity and the acceleration? It is simple. I'll give you these relations directly. The velocity will be equal to negative omega multiplied by a psi omega t plus phi. Again, phi is 0. I will not put it again. Just to make you feel comfortable. This is the velocity as a function of time. What about the acceleration? It is negative omega squared a cosine omega t. It is the same as the position, but we have negative omega squared. Again, omega is equal to 2 pi f, which is equal to 2 pi over tau t, which is equal to the square root of k over m, and it will be equal to something else now for the pendulum motion. We use the differential equations, but we don't use it. I just tell you how we reach this relation. But just to show you. But it is not required. The position, the velocity, the acceleration are given. If I ask you if we have a mass m, and I ask you about the position, you can tell me. If I ask you about the velocity, you can tell me. If I ask you about the momentum, yes and no, from the velocity, p as a function of t is equal to the mass multiplied by the velocity, as we know. If I ask you about the force, it will be ma. It's given. We know that from before. So physics is the same, but now we have a different quantity. All the physics, even the PhD physics and the research physics, the origins of all physics, quantum physics and relativity, any physics you need to talk about. This is the origin of it. The position, the velocity, the acceleration, and the relation with the momentum and the force and the work, because the work is equal to F multiplied by X. This is F. This is the work. Then we have kinetic energy and we have potential energy. This is all the physics in our life. Now we are talking about this. We have an example now. Look, page number 5, we have example. We have a mass equal to 2 kilograms. Okay, what else? It's a spring mass system, not just spring alone or mass alone. It is spring mass, M with K. So we have these relations to use. Yes, and the relation is given to us. X of t is equal to 7 in units. It is centimeters. It is position. The sine and cosine doesn't have any unit. What is the unit of sine? It is not meter, not second, not nothing. It is just cosine 40. I put here pi over 2. This is 5. 5. Because I start not from 0, I start from pi over 2. But again, always I need phi to be 0. Okay. Okay. I need to ask you about amplitude. Where is the amplitude? Who can tell me? How much the amplitude? How much omega? Who can tell me? Online. Any answers? Hello? How much the amplitude? A. Simply. A 7 centimeters. Omega. It is 4. Its units. Radian per second. What else I'm asking about? The angular frequency, omega, the starting angle, which is pi. The spring constant and many, many things. Let me. What if I ask you about the frequency? It is equal from there. Omega over 2 pi. Omega is 4 over 2 pi. Hertz. What if I ask you about the time period? It is 1 over f, which is 2 pi over 4 seconds. What if I ask you to find the velocity and the acceleration? Yes, Salam? Okay, the velocity as a function of time is equal to negative omega. Omega is 4 multiplied by a, which is 7, multiplied by sine, not cosine, sine omega, which is 4t plus phi, we have it pi over 2. What about the acceleration? It is negative omega squared. Omega is 4. It is 4 squared, which is 16, multiplied by a, which is 7. Again, cosine, not sine. If you multiply by the mass, it will give you the momentum. If you multiply by the mass, it will give you the force. Okay. Now we'll talk about any question about this? Take your time to, right? So we have the relations here. I will not remove them. Can I remove it? Now we have the pendulum system. I'll keep everything. The pendulum system. The central pendulum, which is a string with a mass. The string has a length L, massless, without any mass. And this mass is just vibrating like this. It's the string, my string now is black. You can't see it. We don't need to see it because it's massless in our system. We don't need it. It's here. Okay. And this is our pendulum. Just like this. It is a simple harmonic motion. If we look from down, we can just see the motion going to the right, to the left, to the right, to the left, which is a simple harmonic motion. If If we try look to the first half of this page, it's the derivations. We have the gravity downward, mg. We have the tension force here. We have the length, we have theta, we have something. Then we have the final equation like this. d2x by dt squared plus g over L x equal to 0. If you remember, we just write it here. d2x by dt squared plus k over m x equal to 0. We say this is omega squared. And it is a differential equation, and its solution is cosine with a minus cosine omega t plus phi. We need phi to be 0. This is x. It is the same equation. But omega now has a different value. We have the same relations for the pendulum. But omega now, its value is g over L. Not k over m, it is g over L. We have the same thing. The position from the origin here, it is x. The velocity, we have acceleration. We have momentum, we have force. We have the same equations, the same thing. Amplitude, the amplitude is the maximum displacement from the origin. This is the amplitude. The spring system, if you remember, this is the spring system. We have a mass, and the spring is here, and it is vibrating between these 2 points. This is the amplitude. This is the same amplitude. Here we have K, here we have L. We have the mass, we have the gravity. Any question about it? And in the 7th page, page number 7, we have just to complete these relations. This is the same relations. In the last half, or the next half of the 7th page, you can see the 2 systems, the spring and the pendulum system. I will share the monitor. Maybe you didn't print your what? Where's the sharing? Can you see my monitor live? Hello? Nobody?
Yes.
Okay, look now, we have tomorrow the gravity and waves, and we still have the fluids and temperature and heat. They will be fast for 2 lectures, and the next week we have the review. Periodic motion, okay. Put this. As you see here, we have the spring and the pendulum. It is not totally clear when I zoom it. I will put the other one. Okay, now we have for the system and the pendulum systems, we have the same position, the same velocity, the same acceleration relations. What is the difference? The difference of the definition of omega. This is k over m for the spring. For the pendulum, it is g over l. The frequency, the time period is the same, but the quantity inside the square root is different between them. That's it. Okay. Now we'll talk about the energy. As I told you, we have everything as we studied from before, but we have different definition for the energy and the work and stuff. We are on the last page. We just spent 1 hour. Okay, the energy of this system. For the simple harmonic motion. As you know from before, the mechanical energy is equal to the kinetic energy plus the potential energy due gravity, for example, plus the potential energy due spring or elastic potential energy. Okay. Now, for the spring system, we have the gravitational potential is 0 if we are at the origin level or the 0th level. We have the K with the mass. So the potential energy is 1/2 kx squared. The kinetic energy, we know it from before. Simple, 1/2, I will write it here. So the mechanical energy is equal to 1/2 the mass multiplied by the velocity squared, plus the potential energy due the spring, which is 1/2 kx squared. We have x, we have v. Just square them and put them here. Okay, we have 1/2. The mass is m. The velocity, it is negative omega a sine omega t without any phi squared plus 1/2 k x, that is x. It is a cosine omega t without any phi squared. Okay. I'll remove this thing. I need to keep this relation there just to show you we just have this relation. We don't have anything else. Okay, square them, square everything. So E or mechanical energy. 1/2 over 1/2 m. The minus squared is positive. Omega squared, it is omega squared. A squared, it is a squared. Sine squared something, it is sine squared. Omega t plus 1/2k a squared cosine squared omega t. We have two terms, sine and cosine squared. We have m omega, we have k, we have a squared, but remember that omega is equal to k over m square root, but if we square both of them, we have omega squared is equal to k over m, or m omega squared is equal to k. Okay? M omega squared, this is k. So we have 1/2 k a squared sine squared something plus 1/2 k a squared cosine squared, the same thing. This is the energy. We can take 1/2 k a squared as a common factor and we replace with this. sine squared plus cosine squared, how much is this equal to? It's equal to 1. Sine squared plus cosine squared for the same thing, it is 1. So all of this is equal to 1. So the energy or the mechanical energy is equal to, this is mechanical, 1/2 Ka squared, which is equal to, if you need, 1/2 m omega squared A squared. We can use the mass with omega squared or K. This is our energy. We found it by using the kinetic energy and the potential energy for this system. And you can use it to derive also the energy for the pendulum, but it's okay. Like this. This is all I can give you. For the previous example, we have omega equal to 4 radian per second. We have A is equal to, how was A? How much A? It is 7 centimeters. And the mass was 2 kilograms. It is simple. How about the energy, the mechanical energy? You can't find the kinetic energy. I show you how to do that. The mechanical energy is equal to 1/2. The mass is 2. Omega squared, it is 4, which is 16. A, it is 7 centimeters. This is 7 centimeters squared. I need to put it in meters. Okay. So it's just like that. Okay. This is from the exam before. Okay. Any question? Online, any question? Okay. Yeah. You have the notes. You need to put just some notes on them. If we are done, then it's that's it today, and see you tomorrow. I will end the recording.